Hi, welcome to another lecture on precalculus. Title of the section is Values of Inverse Trigonometric Functions. However, I'm going to use it as a lecture on arcsine, arccosine, and arctangent. So as you see, I've drawn three pictures here. There's a unit circles. Uh, some of the famous angles are listed on the circumference. For the sine, you'll see that I am listing them on the right half. For the cosine, I'm listing them on the upper half. And for tangent, again, I'm listing them on the right half. So as far as values of inverse trig function concerned, it is straightforward. Look up our table. For example, if you want to find arcsine of minus a half, here is minus a half. Arcsine means what angle is it whose sine is going to be minus 1/2 with certain restriction. And the answer is minus pi 6. How about arc cosine of radical 3 over 2? Arc radical 3 over 2, what angle is responsible for it? Well, it's pi 6, and the answer is pi 6. How about arctangent of minus 1? Here's minus 1. The angle responsible for it is minus pi over 4. And similarly for any of these other values. Of course, if we are not dealing with these famous angles, then we are going to use our calculator to figure them out. And where does calculator get it from? Well, you have to wait until calculus 2, and then you will see the trades, secrets of the trade. So as far as the values are concerned, that's all there is to this lecture. But as I said, I'm going to use this as an occasion to go over inverse functions. We are going to review inverse functions, then come to inverse of trig functions, and then that's going to lead us to these three pictures that you see. So for example, you might be wondering, well, what happened to the other half of the circle? How come you don't pick any angles there? In all three cases, half the circle is missing. Why is that? And we are going to answer those questions and some others. So let's go ahead. Just as a quick review, what was the deal with the inverse function? We talked about that at the very beginning of the semester, but let's go back and take a look. So it's a quick review of the issue of inverse function. Let's take a function, easy function, f of x is equal to, say, x cubed. What does this function do? Let's take an example. So if you start with 2, of course, it's going to produce an 8 as output. Now, what function is going to do the inverse, meaning taking 8 and gives you the 2 back? Well, that's, of course, the cube root function. If I have the cube root of x, that's a function that does the job of taking an 8 in and giving a 2 out. How are we going to refer to this? Standard way of referring to this is put a minus 1 on top of the name of the original function that you had and read it as f inverse of x. This is a notation that comes with a little bit of a fine print next to it, because in elementary algebra, when you write a inverse, you mean by that reciprocal of that number for a number. Or maybe I better write the b so that's readable here, what we are saying, for b being a number. For a function, what is meant by f inverse? Well, this is a bit of a using same notation to mean two different things. When we are dealing with function, more often than not, f inverse means the inverse function in the sense of some activity that takes the output and turns it back to the input. So not to be confused with the inverse that you have seen back in, say, algebra 1. That's not that inverse, it's a more advanced concept. Next up, well, what do the graph of a function and its inverse look when they are compared to each other? Well, if we have, if 2 gives 8, like 2 gives 8 is a point, if this is 2 and that is 8, and the inverse of it, if you start with 8, it gives you 2, so it is going to be more or less a point like this. Meaning, if you have a graph of x cubed perhaps looks something like this. And then at the beginning of semester, we said if we take this and reflect it across the 45-degree line, what we get is the graph of the inverse. So this is the cube root of x, graph of cube root of x, and this is graph of x cubed. So what we learned at the beginning of semester is that f and f inverse are reflections of each other. So if you have forgotten this, go back to the original lecture and review this concept again. Reflections of each other in the line. What line was that? The 45-degree line that is also called y equal to x. So it's the x-axis is our y-axis, and so on. Next, does every function have an inverse function? We said every now and then we come into an issue. Suppose I take a function y is equal to, say, g of x, and say this is more familiar function x squared. X squared, well, this is the more familiar one to you. X squared looks like this, is that right? The parabola or friendly parabola. What's the problem? The problem is that 2 leads to 4 and minus 2 also leads to 4. So if I start from 4, I want to go back. Which one of them do I go back to? 2 or minus 2? So that's the question. Which one is to be picked? If I'm at output of 4, what input was responsible for that? I can go to the right, come down, and say I started at 2 and ended at 4. I could say I had started at minus 2 and came to 4. So if I want to define G inverse of 4, what should I say? Should I say 2 or minus 2? Well, there's no reason to pick one over the other, and for that reason, we say at the beginning, before we get started, is that G inverse, let's write G inverse, because we cannot make our mind, G inverse does not exist. Well, that's unfortunate. We like to take square root. Starting from 4, I want to go back somewhere. And this one says I cannot do it. And why can I do it? Because I failed the horizontal line test. Any graph that fails horizontal line test is it becomes an issue that inverse does not exist. Sorry, inverse does not exist. So what do we do? A rather simple-minded thing we are going to do, which is, well, throw away half of the baby. Okay, so we like this parabola a lot, but it's causing confusion. Let's throw away half of this. Well, which half we are going to throw away is completely arbitrary, but because human beings start with positive numbers first, negative numbers came very late. That's why we have a hard time with it. Genetically, we have a hard time with negative numbers. We are going to throw away half of this and say, okay, we are going to have a restricted square. Restricted squaring function means, okay, to begin with, I just picked the right half of this picture. What's the advantage? The advantage is that when I want to come back, I have only one choice. So if you start at 4, I come back. Where do I come back? I come back to 2. There's nothing to confuse me because there's no other half. And now we say, okay, if I have, let's call this thing some restricted function x squared, with x is 0 or positive, then our inverse of x exists, and that's our friendly square root, and it does exactly what we want it to do, so there's no problem there. Okay, so we practice this one as well. So it's a function, so a function that fails horizontal test, meaning a horizontal line cuts it more than once. We cannot make an inverse out of it. What's the solution? Throw away parts of the picture so that whatever is left does the job for you, but does not create the issue of having multiple choices. A function does not admit multiple answers, and to have a clear-cut standard, you have to do this. Well, now comes the problem. Trig functions fail horizontal tests in a miserable fashion. Why? Because for trig functions are periodic. So if something is periodic, it's gonna cross horizontal line infinitely many times. So let's go ahead and see. So we said we have a sine function looking something like this. So let me draw a sine function. Okay, this is one cycle of it, but the cycle keeps going. So there is a second cycle, and that's not the end of it either. So there is a third cycle, and there is going backward, we have so does this thing pass the horizontal line test? Absolutely not. Look at all the violations. Here are all the violations. Cuts. So pretty much if it cuts, it's going to cut infinitely many times. So we are in a situation a lot worse than it was with the parabola. Parabola, where there were just 2 of them, we get rid of one and the other one is good to go. Here we have to get rid of all but one. All but one. Well, let's make this choice judiciously. We have to cut a huge chunk of this graph, and what is left is going to do the job for us, but without duplication. So what is the recipe? The recipe is to start from this maximum, go all the way to the previous minimum. So you start from minus pi over 2 to all pi over 2, and then you throw away the rest of this picture. So what is good? What's good about this green part? The good thing is that any horizontal line just cuts it once. So you have your trace back to the angle you wanted, but the trace back just gives you one answer, not just too many answers. So for example, this is 1. You want to trace it back. It traces back to pi over 2. If you have just say 1/2, it trace it back. Well, that's pi 6. 0 traces back to 0, and so on. So if I have -1/2, it traces back to minus pi over 6. Minus pi over 2 traces excuse me, I misspoke. Let me I was a little bit too automatic. That is let me see, sorry for that. So if I am at -1/2, I am at minus pi over 6. If I'm at minus 1, I trace myself back to minus pi over 2. So we are going back from the output back to the input. So we are going this way and coming back to pi 6. At the 1, I trace myself back to pi over 2. So this green function, green colored function, is a restricted sine. And that green function has an inverse. The inverse of trig functions, they have two options. One is just the option we had for all the functions. So if you have a sine, the inverse of it is going to be sine inverse. Okay, inverse of sine is called sine inverse. And let's practice. Sine inverse of 1 is the angle whose sine is 1, so pi over 2. Sine inverse of say radical 3 over 2 is the angle whose sine is radical 3 over 2. That's what? Pi third. So let's write. This is because sine of pi over 2 was 1. So when we want to turn this table around and go from the output back to the input, the notation that we use is this sine inverse. Let's write a few others. So sine inverse of 1/2 is, before then like that, let me write radical 2 over 2 is pi over 4. Sine inverse of 1/2 is pi over 6. Sine inverse of 0 is just 0. And if you have any of these numbers made negative, the output is also negative. So to make this thing easier to write, taking less space perhaps, well, 0 and -0 are all the same. Okay, so that is the story of the arcsine. So arcsine, on this vertical here, I have written the numbers. On the circle, we have the angle. So the idea of the arcsine is that we are going from the number back to the angle. That's the idea. We are reversing the direction in which we are traveling. All the way up to here, we had the angle and we were finding sine or cosine or tangent or something of that angle. Now we have the output of that activity. We want to figure out what the angle was responsible for it. Complication we notice is that 1/2 could be coming from pi 6, it could be coming from 5 pi 6, or you can go around the circle and come back here 2 pi plus pi 6 and so on. There are infinitely many angles that are matching against 1/2. We have to choose just one, and the one we are choosing is just pi half because it's the positive and the smallest of all these angles. So more comfortable to work with that than the rest of the options that we could have. So of course it's easier to deal with pi 6 than with 5 pi 6. So that one we threw away, and all the other possibilities we threw away, and that's how half the circle was chosen. So from minus pi half to pi half, that's what we are concentrating on. Same issue with respect to our cosine. Before going there, perhaps I just briefly use this opportunity to also graph our cosine so that our lecture is complete. Suppose the question is, what does the graph of arcsine look like? Excuse me, I misspoke. So this is the x-axis, this is the y-axis, and the question is, what is the graph of arcsine of x? Let me teach you a simple trick to answer this. Just draw the wavy sine function we had, except that this one was wrapping itself around the x-axis. Is that right? It's going up and down against the x-axis. All you have to do here is to go and wrap yourself around the y-axis. So we are going to draw the best we can. So what is this graph I drew? Is x is equal to sine of y. So instead of y is equal to sine of x, if I want to have x sine of y, that would be it. Now we said graph of a function and its inverse are reflections of each other in the 45-degree line. So graph of sine of x, y is equal to sine of x, and x equal to sine of y are going to be reflections of each other. The restricted graphs also are going to be reflections of each other. So the portion that is going to be applicable to our case will be this, that this is the graph of y is equal to arcsine of x. Let me write it here. This is y is equal to arcsine of x. So again, what happened? We had the x and y axis. The red one is the graph of sine wrapping itself around the y-axis. What's the equation of that? The equation of it is x is equal to sine of y. We just exchange x and y, that's all. The piece of that corresponds to this green piece that we had here. That is, if you take that green piece and reflect it across the mirror, you get this one. And that's the graph of y is equal to arcsine of x. Okay, now let's go repeat all of this discussion with respect to cosine. So we want to talk about what is arc cosine of x. Another notation for that would be cosine inverse of x. Is that right? So we have two notations for trig functions because we are recovering angle. For that reason, the word arc is used at times. On your calculator, also depending on what brand and model you use, some of them have the word arc written on it. Some of them have labeled with this minuses on it. So you have to check to see which one you have. So what was the graph of cosine? Graph of cosine was graph of cosine started at high, came to 0, took a dive, came back up, went up again, and remember this was 0, pi over 2, this was pi, and this was 3 pi over 2, and this was 2 pi, and then it repeated itself. So it came down again, up again, and so on. So does this thing have an inverse? No, absolutely not. Absolutely not, because it violates the horizontal line test miserably. It just we want one intersection, and this gives you plenty. And if you go backward, well, there's some intersections there as well. So strictly speaking, it does not have an inverse. So what do we say we do? Well, we cut a portion of it and restrict ourselves to that portion, and that portion is going to be the restricted cosine, and that one is going to have its inverse. So what is the choice here? So notice that I cannot go left and right because that's already violating the horizontal line test. So I have to go on one side, and the traditional choice is the following. We go from 0 to pi. This portion of cosine does not have the violation of having multiple intersections. Every horizontal line at most has one intersection with this thing. So everything else is out of the picture. We are taking the rest of this graph and crossing it out, and what is left here from here to here, we are going to call it restricted cosine. That restricted cosine has an inverse, and that inverse is referred to as arc cosine or cosine inverse of x. So if you are at 1, you come back to 0. Cosine inverse of 1 is 0. Is that right? Now, how about 1/2? 1/2, what angle whose cosine is 1/2? Well, we say it was pi third. So, and so on. We say cosine inverse of radical 2/2. What angle was it whose cosine was radical 2/2? Well, that would be pi 6. What is the cosine inverse of radical 3/2? Cosine inverse of radical 3/2 is going to be, excuse me, I made a mistake here, pi 4. Cosine inverse of radical 3/2 is going to be pi 6. How about cosine inverse of 0? What angle is it? Well, this is easy to see. At 0, where does 0 come from? 0 matches to pi/2. Cosine inverse of 0 is pi/2. How about cosine inverse of -1? Cosine inverse of -1, that's easiest to see. That matches cosine inverse of -1, that matches to pi, and so on. So how do you graph arc cosine? Again, to get this thing drawn easily, think about doing the cosine of y. X equal to cosine of y. X equal to cosine of y is the cosine that is a trig function that is wrapping itself around. So let me draw another one here so that we have room for it. So they take this wave and wrap it around the y-axis. That's the graph of x is equal to cosine of y. Okay, we usually do y equal to cosine of x, but there's nothing to prevent us from doing the other equation. Okay, now what we want to do, we want to just pick that restricted piece. The restricted piece is going to come from here and just go over there. So the graph of arc cosine, this is the graph of y is equal to arc cosine of x. Kind of a little bit of featureless thing, and it's hard to kind of get lost in it. The best thing to do is to graph the entire cosine curve, x equal to cosine, and then just pick the piece of it that goes from 0 to pi. So important thing was that we are limiting ourselves to 0 to pi. So in this picture, so why is it that we are not looking at the bottom half? Because we don't want to have duplication. We don't want to have pi 6 matches to excuse me, radical 3/2 matches to pi 6 as well as minus pi 6. We have to choose one, and the standard thing is to choose the upper half. So that's why the upper half is here and the bottom half is thrown away. And also the idea of going around the circle and looking at all the coterminal angles, we are throwing all of those away as well, just so that we have one answer. The story repeats itself with tangent as well, but let me just bring an issue with you. Okay, we are always focusing on these friendly angles and everything, but of course we have to going to grow out of that. By the time you go to calculus, every number, every angle is a fair game. They don't have to stick to all this rosy scenarios all the time. So you want to have a way of ballparking an angle. So if somebody gives me a number such as say 1/3, any number, and they ask me what's the arc sine of 1/3, Well, it's easy. You come on this unit circle, whatever number they gave you. For example, if they gave you 1/3, so okay, I draw 1/3, I go to this circle, and I come back here, and this angle is sine inverse of 1/3. So I have an idea what angle is it that we are talking about. Same issue here. If they give me a number, and then I want to visualize what's the arc cosine of that number. So suppose again they gave me 1/3, and I want to figure out what is arc cosine of 1/3. Now here I go straight up. So important thing here, we went on this vertical and traced ourselves back. Here I go on the horizontal, go straight up, connect that to the origin, and that is the angle that's so that is going to be my cosine inverse of 1/3. Okay, so you want to have a way of visualizing these angles. Now let's go and repeat all of this thing with a tangent. How do we handle the tangent? Where does this picture come from? So this picture also drawn so that you can kind of figure out what the arctangent is by visual inspection, have a sense for what that thing is, other than just looking up numbers in the table or punching something on a calculator and looking at some screen. You want to have some analog feel for what this thing is to understand it. So if I have, for example, 1/10, and I want to know what's the arctangent of 1/10, here is the trick to do this thing. You draw the unit circle, you draw this line tangent to the unit circle. Is that right? Go ahead and find the whatever number you are interested in, such as say 1/10. Okay, 1/10 is not a one of those famous angles or anything. You want to know what's arctangent of 1/10. You connect this thing to the origin. You look at this angle, and that is what you are going to be looking for if you're dealing with, say, arctangent of 1/10. Why is that so? Because tangent of this angle is the ratio of the opposite to adjacent. Adjacent is 1, so that opposite is the tangent. And that's why we went and separated 1/10 on that line. So let's go ahead and do a quick discussion on apparently is not letting me. Let's see if I can insert some so let's go discussion of y is equal to arctangent of x. So tangent, we didn't deal with it as much as we did with sine and cosine, so I'm going to just quickly remind you what was the story of tangent. If you remember, we had asymptotes for this thing. So we had an asymptote at minus pi over 2 and then pi over 2. So there are these asymptotes at odd multiples of, so there is a pi here, and there is 3 pi over 2, and so on. And then we had the graph of the tangent. So I'm drawing y is equal to tangent of x first. Tangent of x look like this. Go further down. These things approach their asymptotes. Okay, how about the horizontal line test? Well, this one fails the horizontal line test too. Again, all trig functions are periodic, so all of them are going to fail the horizontal line test. So what? Well, we don't want duplication, and to get rid of that, we have to get rid of this tile and the tile before that, and the restricted tangent is going to be this. The central tile is going to be our friend. Central tile is going to be, so this is going to be restricted tangent. This is going to be the restricted tangent function. So if we want to have inverse, it's the inverse of the green one that we are going to call the arctangent. So y is equal to tangent inverse of x, also written as arctangent of x, is the graph of this green, is the inverse of this green function. How does its graph look like? Well, it's some interesting features. The so-called vertical asymptotes that we had here, if we reflect them across the 45-degree line, they are going to become horizontal asymptotes. So we are going to have a horizontal asymptote at pi over 2 and another horizontal asymptote at minus pi over 2. And this picture is going to flip over. That is going to look like this. So just like the other ones, we have to draw x equal to tangent of y. That's going to be several of these blocks going up and down, and we are just choosing the central one as our chosen piece. So this is the graph of y is equal to tangent inverse of x. So for example, what is tangent inverse of infinity? So if you go all the way to infinity, what's tangent inverse of it? What's the angle responsible for infinity? The angle is pi over 2. This is pi over 2. What is the tangent inverse of 1? What's the angle whose tangent is equal to 1? Well, that's the easiest one. That's going to be equal to pi over 4. What's an angle whose tangent is equal to minus 1? Well, that's going to be minus pi over 4. And that is what we captured in this picture here. So again, you see that we are focusing on the half of this circle. The other half is skipped because we don't want duplication. And the way to use this thing for getting a visual sense of arctangent of a number is that say if I want to find arctangent of 2, or well, let's choose a different number so it fits here, say 1.5. So what's arctangent of 1.5? So I go on this, this is 1. I go 1.5, wherever that happens to be. I can't connect that to the origin. Look at the angle here, and that's going to be my arctangent of 1.5. Okay, so we covered quite a bit details of these three functions. It takes quite a bit of time to actually get used to it. However, answering the questions here is almost trivial in comparison with understanding what these functions are. And you need to understand these functions because they are going to be with you all the way through calculus 1 to 3 and all the other classes you're going to be taking. There's going to be references to these. So tangent inverse of 1, how do we well, you want to make a table for these things or redraw these circles as this paragraph better than a table. Redraw. So tangent inverse of 1, tangent inverse of 1 is pi over 4. Okay, so draw the picture and also make a table so that you see actually pi over 4. So what do we do? Draw the unit circle in all of these cases. That's going to help plenty. For tangent, draw the tangent axis. This is the tangent axis. So the radius also is 1. On that tangent, the number that's given is 1. Here's 1. On this tangent axis, that's the one. Connect to the origin. If you draw this picture reasonably, you can just see that this is 45 degrees because this is a square. And 45 degrees, of course, pi over 4. So you want to understand why this thing is pi over 4. If trying to memorize them might not work all that well. You have to have a visual impression. So tangent inverse of minus radical 3, we might as well use this. This is minus 1. If you go all the way to here, well, that's going to be minus 2. And here we are dealing with minus radical 3. So to draw it accurately, just get a sense of where is minus radical 3, like minus 1.78 or whatever it is. So question is, if I connect this to the origin, what is this angle? Well, now I'm going down here. So what does it look like? So again, if you draw this accurately, you see right away, well, that has to be pi third, but it's in the bottom, so it's minus pi third. So minus pi third. So again, the idea for tangent is that we are using from, so let's go back up here, and so arcsine is going to go from minus pi over 2 to pi over 2. Cosine is going to go from angle 0 to pi. Arctangent is going to go from minus pi over 2 to pi over 2. The two ends are not included because at those points tangent becomes infinity. So okay, so that is minus radical 3. Cosine inverse of radical 2 over 2. So again, how do we get a sense for what this thing is? First of all, we remember, well, we draw the unit circle. Just go ahead and draw the circle. Okay, half of it is what we want. Cosine, we are dealing with this portion. Cosine is the upper. This is what we are dealing for cosine. Now, what is the idea? Radical 2 over 2. Radical 2 over 2. What is that? 0.7 almost. Radical 2 over 2. Get an approximate sense for where this thing is. Okay, we are going straight up, connecting to the origin. And we are talking, what is this angle? If you do it accurately, if circle is drawn accurately, if this radical 2 over 2, what's radical 2 over 2 is about 0.7. Actually go to 0.7, draw this thing, and eyeball this thing. What does it look like? Instead of memorization, so well, that looks like 45 degrees, that's pi over 4, and so on. So try to have a sense about that again, as opposed to just memorizing. But of course, memorization is also good. This is tangent inverse of minus radical 3, which is a duplication of what we did here. Okay, so we covered quite a bit here. The exercises are minuscule compared to the concept. I hope you listen to this several times and get the maximum out of it. Until next time, good luck and God bless.